Hello everyone. I'm very happy and honored to present you today our paper titled An Input Observer-Based Stiffness Estimation Approach for Flexible Robot Joints. Let me first introduce myself. I'm Maja Trumić from Serbia, and I'm a PhD student supervised by Adriano Fagiolini, professor at the Department of Engineering at the University of Palermo in Italy, and by Kosta Jovanović, professor at the School of Electrical Engineering ETF at the University of Belgrade in Serbia. Let me now reveal you the motivation behind our paper. Robots with flexible joints, that are robots with elasticity concentrated inside their joints, have become quite popular recently. Actually, the main advantage of these robots is that besides position, they can also change the stiffness in their joints. It is well known that if you can change the stiffness in robot joints, you actually also affect the stiffness of your end effector. Consequently, this makes those robots safe for the physical interaction with humans. So how can joints change their stiffness? Well, actually, they have variable stiffness actuators. And with the development of robots with flexible joints, also variable stiffness actuators have been developed. Nowadays, we have novel open source and cost-effective variable stiffness actuators that are emerging to the market. The primary application of robots with flexible joints is definitely safe physical human-robot interaction. But those robots are also quite effective when it comes to locomotion tasks or explosive actions. I mentioned that stiffness is very important for these robots. So be prepared for the challenge. Stiffness is not measurable. This leads us to the question, what is the value of stiffness in robot joints? Well, since stiffness is not measurable, we can express stiffness as a function of already available data of a robot. So we can either perform offline identification procedure, but we all know it is time consuming. Another way is to use a model of stiffness, providing a datasheet from the manufacturer of a variable stiffness actuator. However, temperature drift and the various springs might affect the accuracy of such data. So in this paper, we propose a smooth solution, the online estimation of stiffness. Let us now go into details of one flexible joint. Here in the picture, you can see bidirectional antagonistic actuator of a flexible joint with the electric drive. That means that we have two DC motors that are connected to the flexible joint via nonlinear springs. The mathematical model of this system is provided here, where the first equation describes the dynamics of robot links, and the second two equations describe the dynamics of two motors. The handy property is that the total elastic torque acting on the joint is actually equal to the sum of local elastic torques generated by each motor. By definition, stiffness in the joint is equal to the partial derivative of elastic torque with respect to transmission deflection. That is equal to the difference between the angle of a link and the angles of two motors. So finally, we can conclude that the stiffness in the joint is equal to the sum of two local stiffnesses. This property allows us to approach this challenge from the motor side. This means that considering this set of equations, we can actually concentrate on a single motor dynamics. Another advantage of this approach is that it doesn't suffer from the lack of observability, which would be the case if you would approach the problem from the link side. Now let me tell you the main idea in steps. First step, consider the ith single motor dynamics. Then design a delayed unknown input observer to reconstruct flexibility torque. In order to design unknown input observer, we need to rewrite motor dynamics in the state space form. And the main idea is actually that flexibility torque is taken as an unknown input to the system. So we use unknown input observer to reconstruct this unknown input. I would also like to draw your attention to the fact that the outputs are positions of motors and commanded torques of the motors. And finally, we use the Recursive Least Square algorithm to estimate stiffness. The machinery behind our paper is contained in those 5 words, the delayed unknown input observer. These observers are usually used for fault and defect detection in linear systems. The philosophy is that you should do dynamic inversion of the system in order to simultaneously estimate states and reconstruct unknown inputs. So if you have a linear system in the state space form like here, that is the system of our DC motor, then dynamics of observer is provided in these equations. And you can see that for the estimation of unknown inputs, we need estimation of system states here. So for the states estimation, it is necessary to design those matrices E and F. The design procedure is described in our paper, and also it is provided in the work of Professor Sundaram. Another term is this one that denotes L, last outputs of the system. So what is the role of these delayed outputs? Actually, these delays allow us to relax the conditions for designing the observer. So in our case, we do not need velocity sensor. The main advantage of using unknown input observer is that we can have a complete lack of a priori knowledge about the unknown input, in our case, flexibility torque. However, the disadvantage is that we need precise knowledge of dynamic system matrices A, B, C, and D. Once we estimate flexibility torque via unknown input observer, we can also, we should now find what is the value of a local stiffness. It is well known that the approximation of a flexibility torque can be expressed as a function of powers of transmission deflections. And by leaning on the definition of stiffness, we reach this expression for the local stiffness value. Now it is clear that we need to estimate the value of parameters P1, P2, P3, and P4. And we perform online estimation of those parameters by using recursive least square algorithm. So to conclude, the data from sensors that we need are positions of motors and links and commanded torques to the motors. Now the interesting part, experiments. We performed experiment first on 1 degree of freedom robotic setup that is actuated by QB move variable stiffness actuator. Experiment is designed in a way that it has 3 phases. In the first phase, both position and stiffness are changing. In the second phase, position is changing and the stiffness is constant. And in the third phase, position is constant while the stiffness changes. So what are the results? You can see in this figure that during the first and the third phase, the estimation of both flexibility torque and the stiffness is pretty well. Well, maybe except for this initial part, which is due to the fact that we initialize parameters of recursive least square algorithm with zeros. So in the beginning, we actually have complete lack of knowledge about initial value of those parameters. And that's why the algorithm needs some time so that the parameters can converge to values that provide a good approximation of torque and stiffness. However, in the second phase, we notice that even though flexibility torque is well estimated, there is some drift in the estimation of stiffness. So why does it occur? It occurs because there is a lack of excitation for the recursive least square algorithm. So since stiffness is constant and only position is changing, there is not enough excitation. The mean square error for the flexibility torque estimation, this experiment is 10 to minus 5, and for stiffness it's 10 to minus 1. So how can we prevent this drift in the estimation? Well, we can assume that parameters during the first phase, when the excitation is good enough, they already converge to the values that provide a good approximation of torque and stiffness. So simply, we can stop the update at this moment. And this is the result. So it's a fantastic now estimation of flexibility, torque, and stiffness, and it is also proven by mean square error, which is 10 times smaller. Then we also performed experiments on 2 degree of freedom setup. The commanded position and stiffness for both joints is the same, and these are the results. So both flexibility, torque, and stiffnesses are estimated well, and by performing these experiments, we proved that our approach is applicable also for multiple degree of freedom robots. So thank you very much for your attention. Feel free to contact me at my email address if you have any question, and goodbye.